A very good morning, one and all present. On behalf of trustees, management, principal, HOD, staff, and students of SA Engineering College, I extend a warm welcome to one and all present in this virtual platform organized by the Department of EC and VLSI. To know more about our college, SA Engineering College was established in the year 1998 and is successfully continuing its educational service beyond 25 years of excellence. The college is approved by AICTE New Delhi and affiliated to Anna University, accredited by NBA and has an A grade from NAC and also ISO certified institution, which fosters development of young minds, nurturing curiosity and critical thinking. It has been a effort to create unique and engaging learning experience. Tech Series is one such achievement.
I feel honored to welcome our resource person of today. It's my privilege to introduce esteemed speaker Mr. Ramakumar Meghanathan, who currently works as a partner enablement manager at Microsoft, operating temporarily from India. With over 15 years of experience in the tech industry, Mr. Ramakumar has held several key positions at Microsoft, including partner business manager, support escalation engineer. Before his time at Microsoft, he contributed significantly at Wipro Limited as technical head, technical consultant for Microsoft Exchange servers. Academically, Mr. Ramakumar holds a Master of Science in Communication Network Planning and Management from the University of Portsmouth, UK, and a bachelor's degree in ECE from SA Engineering College. His cross-functional leadership, stakeholder engagement, and commitment to partner success contribute to make a meaningful impact across Microsoft's partner ecosystem. With a strong foundation in project management and requirement analysis, he now enables Microsoft's global partners to scale, innovate, and succeed. On behalf of our department, we are happy in welcoming you in the virtual platform, sir. I now hand over the session to you.
Oh, thank you so much. Sorry, I was having some trouble with my mic. You guys able to hear me? All okay?
Yes, sir, all okay.
Perfect. Let me see if I can turn on my cam. Good morning.
Good morning, sir.
All right. So as you know, I'm an alumni for SA Engineering College. I did my bachelor's there on electronics and communication faculty. After completing my studies, I did fly abroad to complete my master's in computer network. And there is a backstory why I chose network, and I really wanted to share. Um, I remember in my sixth semester when I was having my computer networks, I did have an arrear. I failed the subject, so I had to redo my exam, and I did. I'm not sure if you guys know, but there is a author called as Ferozon. So he was the one who authored the computer networks book. So I read that book end to end just to clear the examinations, but I fell in love with networks. So that's how my journeys towards network started. I flew back to UK to complete my master's degree. After completing my master's degree, I did work as network engineer for quite some time, and then joined Wipro in Chennai as a technical consultant. Moved up my ladder, moved as a technical aide, and then from there I moved here as a technical advisor. Worked as an escalation engineer, and now I'm a business manager for Microsoft. I have close to 10 years of experience in Microsoft, and previously I had like 5 years of experience altogether. But with that, today we're going to talk something which is not an usual conversation that I do have over the calls, but it's going to be an experience for me. In case if I do miss up, do let me know. Let me see if I can share my screen, and do let me know if you're able to see the screen. Is this visible?
Yes, sir, visible.
Perfect. Okay, fantastic. Give me a moment. Today we're going to talk about signals to quantum. Right? That's exactly where it all started. So historically speaking, the electronics birth started with zeros and ones, signals, wires, right? That's you pass on the electronics or electrons in simple terms. that gets converted into signals by the numerous wave, sinusoidal, trapezoidal, whatever you think of, right? So the digital waves that sends across. And that's how you communicate. I don't want to complicate because I know the audience are from, you guys are not at the engineering graduates. So I'm going to keep it simple. But in case if there is any questions that you might have, do let me know, because I really, really, really wanted to ensure that you guys have all the information that you needed and you get inspired from what is absolutely necessary for you to know if you're choosing the right degree or right faculty. Okay, with that being said, how do I move on to the next slide? Once again, sorry, I'm not used to Google Meet. They are my competitors, so I use a different thing. Does it change? No? Give me a minute. Okay. Did the slide change?
Yes, sir.
Can you see? Can you tell me what you see?
The first signal.
Perfect. Okay, thank you. So I want to start with the topic, the first signal. Of course, I joined electronics and communication engineering because I kind of fascinated about how the electronics works. Like, the back in days we had radios, tape recorders, Walkman. I'm not talking about the phone Walkmans. I'm talking about the real hardware Walkmans. And then TVs, televisions. We had CRT, and then that got converted into LCD. Back then we did not have LED; it was LCD, right? So my first journey started with that. I knew that there are a lot of opportunities that is available when it comes to electronics, because even if it is computer, it has to run on an electronic, right? So that's exactly where it all started with. So first project of mine is having the breadboard. I'm not sure if you guys know what is breadboard is. The picture shows it. It's a white bread slice like a thing that you use in the lab. So that was the first project. I had to connect some numerous electronic devices. You call them as resistors, capacitors, potentiometers. So there are multiple, right? I did not know the name of it back then. So I just had a whiteboard. So I had an opportunity to connect some of the electronic particles and then have an LED glow. And of course, I'm not sure if my lecturers remember this, but I did burst one of the circuits. The entire building was shut down. There was a power cut because of that. I didn't know that I was using an I resistor back then, and it got short circuited, and then I had to lose the power for the entire building. Luckily, I was not detained for that. Detain is like your HOD will give you a warning or probably suspend, right? That did not happen with me because we are in the world of exploring. So thank you so much, the lecturers that I had opportunity to work with. They did not detain me. I don't think I've been scolded. But yes, it's an experiment. So they allowed me to do what I wanted to do and learn from it. Right? Yes, that's exactly how it started. So when the first project that I had, the breadboard with the LED, with all those electronic parts that we have, like resistors and capacitors, I was fascinated, right? I started getting more curious towards what does this do, right? These objects, what does it do, right? And where does it take to, right? And with that, I'm going to be starting our actual topic today, that is from signals to quantum. But before you know what is signals to quantum, I wanted to start with the power of electronics and take it from there. So the electronics has revolved around multiple components inside the world of electronics, but electronics has evolved by shrinking in size, right? The whole idea of electronics is whatever you have it as big, make it as smaller as possible. So that's how it is. So we started shrinking in size, but it increased in intelligence, right? And it's expanding in connectivity. That helped us to transform from isolated circuits that we had back in days, probably in 80s before that, to globally connected smart systems now. Now, when I say analog circuits in the slide, I can give you an example. you know, the tape recorders or receivers that your granddad used to have. So that is a radio receiver, right? So that uses analog circuits inside it. All you could do is it can transmit. It has transistors and capacitors, so you can tune into the some of the signals and probably get you there what you needed, right? But the analog system process continuous signals, and that is the first laying of foundation for the communication and control. Like, have you ever imagined how does the AM circuit works, or AM radio receiver works? So you sit in some remote location, you have an antenna pointing towards sky. You just scroll the button, and then it makes the trick. So it makes you to read the signal, that's frequency, right? So it reads the frequency and then provides you with the song or information or news, whatever you needed. From there, the analog circuit led to digital signals, right? The digital systems that we call. And maybe I might be able to relate with you guys with this word, because you would have seen calculators and early computers. Probably you guys are not too old. So you probably would have seen the microprocessors. You would have heard about microprocessors that we use in calculators and early computers that uses the binary logic, right? So that's the digital system. So digital electronics introduced the precision. It ensured the programmability is easy, and you can scale exponentially, right? So that's the birth of digital systems, right? The wireless and all of the stuff. And then that gave birth to embedded systems, or the embedded processors, right? We call that as microcontrollers. You are using microcontrollers in almost every single device that you touch today, right? Washing machine, refrigerators, even the thermostats that you have. So everything as the embedded processes, right? So the embedded system brought intelligence to everyday devices, like I said, and it enables the automation and control. So that's the benefit that we moved from. So now you imagine we had an analog circuit just with resistors and capacitors that allowed us to receive the signal, and then from there we transitioned into microprocessors where we could be able to do the calculations and the computers to process our request. We had given birth to digital electronic devices back then, and that's how you see all those devices that you use today. Then that laid foundation to the embedded systems. All your washing machines, refrigerators that you are using today is purely based on the embedded processes that you will read in your electronics and communication. Now, what's the future, right? So the quantum computing is the future. So this might be overhead, but quantum electronics aims to solve problems in a very classical computer way, but at the same time, it has the capability to simulate molecules or optimize logistics at scale. When I say scale, imagine having a 1 millimeter of a small ball, but inside India. So that's the scale of it, right? So that can do magic. But yeah, we're going to talk about quantum in deep. So quantum computing is what we're going to have as the future. But what is quantum computing, right? So it's very simple. It's going to advance the field of computing that would leverage the principle of quantum mechanics. So these keywords, whatever I'm saying, if you have any doubts, please do make a note. You guys are having internet in your hands, like through mobile phones and smartphones. Just to read one liner, that's more than enough. That will create a curiosity in you, right? So quantum computing is an advanced field of computing that leverages the principle of quantum mechanics to process information exponentially faster than the classical computers. What are the key principles that we have in quantum computing is the superposition, which is qubits. This word might be off the record, but I will definitely show what exactly the qubit is. So qubit exists in multiple states at a simultaneous time. So imagine in this way, it's it's 0 and 1. It's either 0 to 1 or 1 to 0. But imagine if it's a qubit, it has the 3D dimension of it. So that's exactly how qubit works. The entanglement. So qubits can be correlated over distance. So it has no control on how far or how further it can travel. But at the same time, it can be controlled. It's not like you throw and you lost it. No, it's like something that you can control. Then you have the quantum interference, which uses the used to control the qubit states. That's exactly what I said. So you can control the direction, you can control the speed, you can control the dimension. That's what the quantum interface is meant for. But yeah, here's a quick example of how does you can compare the bits versus qubits. So in classical computers that we use today, we use bits, that is either 0 and 1. That's exactly how you sound. It's like millions and millions of zeros and ones on a binary logic that's been sent across through your classic cable wires, and that gets transformed into, like I said, the microprocessor and controllers that takes care of it in the conversion, and then you receive the signals in the format that you want. That is the application or the interface that you're seeing, that the UI interface that you see. But what does the qubits do? So it's a quantum computer particle that is being used. So it's 0 and 1, and it can be both. It can be both 0 and 1. It's not 0.5. Don't confuse yourself. It's not 0.5. What I'm saying is it can merge with each other. So it can be at 0 and 1 at the same time. That's called a superposition. That has never been achieved in the past. So you can either have 0 and you can either have 1. That's how it has been, right? You can either have your what's a basic example that I can give you. All right, here is it. So you have a light at your home. You have a switch. You can turn it on or you can turn it off. Do you have a superposition in between where it is like combined with each other? That's not possible, but that is possible with qubits. That's exactly what qubits does. So it can be at 0 and 1 at the same time. That's called as a superposition. But it does not lose the value. That's most important. So when you do that, it should not lose the value. I hope that helps, but yeah, here it is. So more about qubits. So qubits are a basic unit of classical information representing 0 or 1, but qubits can represent both 0 and 1 simultaneously due to the superposition that it has, like the spinning coin. Do you see the head or do you see the tail or do you see the both? Right? So that's exactly what the qubit does. So the superposition will allow the qubits to represent multiple states at once, enabling greater computational power and flexibility. The entanglement would create a connection between qubits where the state of one qubit influences the another, and regardless of the distance. A better comparison between qubits and bits. So bits are the basic units in classical information, but qubits can represent both 0 and 1 at the same time. Classical bits follows the deterministic rules, while qubit utilizes the quantum mechanics. I keep repeating the quantum mechanics word again and again, but please do read at least a line or two. You guys are enabled with internet, so do read through or watch your videos in YouTube or whatever that's applicable, but that's the future. So quantum mechanics is the future. So the qubit would enable the complex calculations through entanglement, but you just saw in the previous slide, and that would outperform the bits in a certain task. Imagine if a bits could do, and I'm going to give an hypothetical number, like 1 millisecond, then qubits could do in fractions of millions milliseconds. So that's how qubits are powerful, right? So the bits are limited to binary state, but qubits can expand in a computational way. I do have a video, but yes, for the later time. This uses the concept of topoconductor. You would have heard about semiconductors, but you would have not heard about topoconductors, is what I believe. But topoconductor is like a novel class of material crucial for topological qubits, the one that you wanted to create. It combines both semiconductors and the superconductors properties together to enable and generate the qubits. The composition for topoconductor uses indium arsenide, so that's a semiconductor, and it uses aluminum. That's a superconductor, right? So it creates a topological superconductivity between these two layers, and it creates the qubits in between. So the significance of why we use superconductor is because it protects the quantum information from disturbance. So we needed the semiconductor and superconductor to ensure that our quantum, whatever we generate, is not lost due to disturbance, or we call it as noise in terms of like electronics. So that should not be an impact, because like I said, qubits could be in an exponential state. It's not 0, it's not 1, it could be in a superposition. So it's like, it's on a 3D level, it covers everything, and we want to ensure that there is no disturbance. So we definitely need a topoconductor configuration to ensure the qubits are staying intact as it is. This would be essential for building a scalable computing, quantum computing, because like I said, we needed both semiconductors, superconductors, to ensure that we have this topoconductor configuration, so to ensure that we make the computers efficient enough to achieve the results that we wanted. Now, recently, like in this year, Microsoft has released the Majorana 1 chip, and that would reduce the development time for the quantum computers, because until earlier this year, the quantum computing was just a theory. It was written in papers, theories, theses, but it has never been made as a reality. Like nobody saw how the quantum computing is going to look like. We are just talking about quantum. We know that's a possibility, but we were imagining that it's going to take years and years together to build such a quantum computers that's going to exist in the world. But that was made realistic from Microsoft. You're going to see what's Majorana. I will show you the picture. So this is the topological superconductivity that I was talking about. So you have the superconductor and you have the semiconductor in between. Together you join and you make the topoconductor. So that's the difference of the superconductor and the semiconductor. I'm going to share this slide probably, so I don't want to read through. I know we are like just have like few more minutes left. I'm going to skip. I'm going to go to Majorana. So this is Majorana 1, the world's first quantum processor powered by topological qubits we just talked about. So all of this, whatever we spoke about, will go even further with quantum. Earlier this year, we announced Majorana 1, the first quantum processing unit, QPU, built on a topological core. In fact, we have quantum lab within Microsoft. We have a dedicated lab for electronics. So we have a quantum lab that was used to build this. So we believe this processor, what we build, will be a breakthrough and will allow us to create truly meaningful quantum computers, not in decades, not in, like, as I said, it's only on theories, but now it has been made reality, as some have predicted. But qubits are going to be created, and we already created qubits with the topoconductors, and that's going to make us move faster towards the quantum computing. A little bit more about Microsoft Majorana. So Microsoft Majorana represents a breakthrough in topological quantum computing. Majorana fermions are the unique particles. So these words might be Greek for you guys. But like I said, please make note and see if you could read through whenever you have time, because research is all it requires. So key to success is research. So do research, try to understand what it is, and move forward. So Majorana fermions is created using magnetic fields and superconductors. It helps to protect the quantum information from the disturbance, and the topological qubits are more stable, less prone to errors compared to the traditional qubits. Majorana 1 chip, powered by topological core architecture, reduces development time for quantum computers from decades to years. It enables creation of smaller, faster, and more stable qubits. And the impact on quantum computing, I think we did talk about it in the previous slides, but it would enable, and it's a promising revolution that we have created in this field by solving complex industrial scale problems. It offers a path to scalable quantum computing with potential to solve current unsolvable problems. And with that, I'm going to play a video. Let me know if you're able to. Is that audible? Was that audible?
Yes, sir.
Okay, perfect.
What would the world look like with a computer that could accurately model the laws of nature? That's the promise of quantum computing, but there have always been limitations. Now, as one of our longest running research projects, our team at Microsoft has been able to take a subatomic particle that has only been theorized until now, and not only observe it, but control it, creating an entirely new material and a new architecture for quantum computing. One that can scale to millions of qubits on a single chip.
This is not a work of science, it's a work of science and art.
I've got so many ideas are a little science fiction sounding.
It will solve problems unsolvable by the combined power of all the world's compute today, and promises to revolutionize fields such as medicine, material science, and our understanding of the natural world. Our first quantum processor based on this architecture is the Majorana 1. Yeah, I've always been fascinated with puzzles and challenges and a mixture of mathematics and computers. And so when I learned that there was this type of computer that didn't exist yet, but could solve problems that we couldn't solve with our digital, all of the computers we had, I was just fascinated. I wanted to learn, well, how can I help that computer be built?
Over the years, I ran into problems that could not solve on the most powerful computers. But then over time, I realized, hey, I could solve that if I had a quantum computer. A laptop can solve a problem of 10 electrons. A supercomputer can solve a problem of 20 electrons. But no classical computer in the world can exactly solve the behavior of 30 or 40 or 50 electrons.
The number 30, 40, 50 electrons, those numbers are seemingly small, but require up to lifetime in the universe timescales to solve with all of the world's computers operating together. That's until you have a scaled quantum computer that can solve these problems efficiently.
These calculations are so complicated that then if the classical computer was as big as this entire planet, it would still not be able to compute, just to give you a concept of scale. And a quantum computer can do it very, very well.
At the core of a quantum computer are these qubits. Qubits are like our classical bits, right? These are essentially zeros and ones in a transistor. And we need the analog of that in quantum computing. The analog is a qubit, a quantum bit, that serves as that core information unit. It's where we store the information and then we process on those qubits to create computation and ultimately get solutions back out. Now, there's many different ways, right, to create a qubit. The reason quantum computing has been so slow to progress is that the industry has been struggling with problems making qubits reliable and resistant to noise. Progress has been incremental.
The challenge is qubits are actually pretty delicate in general, so you need underlying qubits that are really stable. But you don't want them to come at a cost, because you don't want your underlying qubits to be really big. That's one way to make it more stable, is have them really big. If they're really big and you're still going to need many of them, then how are you going to fit them all into your system? You don't want to deal with something the size of a warehouse. Then the second thing is you don't want the qubits that are being slow, right? Because if the price you pay for getting something stable is you have to go really slowly, then a computation that might take you a month ends up taking you a decade, and that's not useful. People in the early days of computation used vacuum tubes, and then that technology, actually you could build very good computers with it. And then the transistor was invented, and the earliest transistors weren't necessarily that great, but it became clearer over time as the transistor developed and the integrated circuit developed that this was going to be the technology of the future. In that spirit, that the first generation of qubits may not be what gets us to the next stage where we can really solve the kind of problems I was mentioning that are really important. And so we might need to invent a material and therefore a quantum processing unit that has the right properties. So for us, we want something that has some built-in level of error protection. And a lot of those ideas actually were explored in the context of software or quantum error correcting codes, where you can actually build a lot of those ideas into hardware.
So the way you design that qubit matters. We see the states of matter every day. Solids keep their shape, liquids vary but keep their volume, gases expand to fill the space they're in, all defined ultimately by how their atoms behave. But what if there were more? What if, under the right conditions, you could engineer more? States that have only ever been theorized, that would change how subatomic particles actually behave. 100 years ago, mathematicians predicted one such new state of matter, the topological state. And since then, researchers have been looking for a very specific, very useful quasi-particle within it, the Majorana particle. Last year, we were able to observe it for the first time. And this year, we're able to control it and use its unique properties to build a topoconductor, a new type of semiconductor that operates also as a superconductor. With this material, we can build a whole new foundational architecture for our quantum computers. a topological core, allowing us to scale to not tens or hundreds of qubits on a chip, but millions, all in the palm of your hand.
Majorana's theory showed that mathematically it's possible to have a particle that is its own antiparticle. That means you can take two of these particles and you bring them together, and they could annihilate and there's nothing left. Or you could take two particles and you bring them together and you just have two particles. Sometimes it's nothing, the zero state, and sometimes it's the electron, the one state.
So it really has taken quite some thinking, right? Some time to design a device, design a chip that can enable measurement of this literally elusive particle. We've designed a chip that is able to measure the presence of Majorana. Majorana allows us to create a topological qubit. A topological qubit is reliable, small, and controllable. This solves the noise problem that creates errors in qubits. Now that we have these topological qubits, we're able to build an entirely new quantum architecture, the topological core, which can scale to 1 million topological qubits on a tiny chip.
Every single atom in this chip is placed purposefully. It is constructed from ground up. It is entirely a new state of matter. Think of us as building the picture by painting it atom by atom. In a regular chip, the computation is done using electrons. We don't use electrons for compute. We use Majoranas for compute. It's an entirely new particle. It's half electron.
When we look at the design of this chip, right, first of all, you can fit so much on just a small form factor, right? This chip can store over 1 million qubits, right? Over 1 million can fit on just this small form factor. In addition, we don't want to wait centuries or millennia for a solution. And so this chip also offers the right speed to get solutions from the chip in a reasonable, efficient, amount of time. That's the beauty in this qubit design, the topological qubit. It has the right size, the right speed, and the right type of controllability. And all of that together means that it has an ability to scale like no other.
The way this system that we are constructing works is you have the quantum accelerator, you have a classical machine that works with it and controls it, and then you have the application that essentially goes between classical and quantum depending on which problem it's trying to solve. Once the computations are done, the results are resynthesized from the classical side and produced back to the user as one complete answer. Where the quantum machine shines, it is able to do simulations, particularly in chemistry and materials, that are extremely accurate, as accurate as an actual wet lab experiment. Imagine a world where a scientist computes the material that they want, and they compute it to the accuracy that it's first time right. So when you walk into a lab, you don't need to experiment anymore. Imagine a battery that you charge it once and you never have to worry about discharging.
What can you do with 1 million qubits? In the last few years, there's an explosion of artificial intelligence, right? Co-pilots. And what's so inspiring about a quantum computer is that with a quantum computer augmenting the AI capability, it can help more, drive even more discovery.
What makes me excited about quantum computing is that it will give us the tool to tackle many of these challenges at the fundamental level by creating new chemicals, new drugs, new enzymes for food production.
Honestly, it's kind of mind-blowing right now because this is something we've thought about for a while, years or more.
We call the ages of mankind by materials. We've talked about the Stone Age, we've talked about the Bronze Age and the Iron Age, the Steel Age, Silicon Age. Materials define our culture, define our mankind's define our progress. That's what could be more powerful than having a machine that can like even radically change the way we work with materials.
Our leadership has been working on this program for the last 17 years. It's the longest running research program in the company. And after 17 years, when we are showcasing the results, we are showcasing results that are not just incredible, they're real. They're real because they will fundamentally redefine how the next stage of the quantum journey takes place.
We're at the cusp of a quantum age, and Majorana 1 is just the beginning.
I hope that was helpful.
Yes, sir.
Thank you. So we have built the world's first topoconductor qubits making or reliable qubits making quantum processor unit, the one that you saw, the big one, right? So that's the quantum processor unit. Just going to show you that. That's the chip, and that's the unit, right? Okay, with that, I'm going to probably pause, and I'm going to see if there is any questions that's there for me. And is that okay if I can stop the slide? I think so. Okay, I'm going to stop sharing. Back with you guys. Is there a question that you guys have for me?
Participants, if you have any questions or need further clarification, please feel free unmute or use the chat box to share your doubts.
Oh, there is a chat box?
Yes, sir.
Oh, in comments. Okay, I don't see any questions in the chat. Cool. If there is no question, here is my request for all aspiring engineering graduates or existing engineering graduates. Be curious. Try to do research. Whenever you see something that is not understandable, try to do research. Try to experiment. Don't be afraid about failure. Don't be afraid about asking questions, because only when you ask questions, you will get an answer. Nobody is going to feed you or spoon feed you in the real world. I mean, that's possible in your school. That might be possible in your college, but that's not going to be possible in the real world. So start asking questions. Please go ahead and try to do research as much as possible whenever you have something that you do not know, because you have the computer in your hand, right? So right in your front of you. So just try to search, do research. If you have any questions that you had regarding this topic today, probably reach out to one of your hosts and they might get back to me. With that, do I drop off? Geeta ma'am, are you still there on the call?
Yes, Ram, I'm here.
Okay, perfect. Let me know if there is any questions. I will be happy to address any questions that might come up from the team. And I do see there is no questions from audience. I'm not sure if I confused them. I'm not sure if it was beneficial for them. But yes, it was so happy for me to connect back with my lecturers, my professors, my college in very specific. I'm proud of being one of the alumni for this college, because that paved way for my success. There is a lot more to go, I would say. In the world of electronics, in the world of computing, there is a lot to go. And I'm going to close my thoughts with one final word. Computer does not exist without electronics. So we thrive on electronics. everything that we touch today, everything that we do today, even the wireless, whatever we talk about, does require electronics, and that's the base for all the computing that we just spoke about, the quantum that we spoke about. Thank you so much. Thank you for having me. Until next time, take care. Bye-bye. Study well. Enjoy.
Thank you so much for your insightful session, sir. Your talk was truly informative and inspiring. We are grateful for your valuable time and knowledge.
Thank you, ma. Thank you. Take care.
I kindly request all the participants to take a moment to fill out the feedback form. Participants are requested to fill the feedback form.